Welcome back. Here are two pieces from two very different musical traditions, and I want you to think about this. What makes them different? That was Vivaldi. That was Vivaldi's Spring from 1723. Here's a piece from a very different musical tradition. What makes these pieces so very different? How can we quickly distinguish Western music from Chinese music? That was a piece called Lady Mengjiang. Why is it that mathematics plays a role in this difference? Now, there are of course many differences between music from different cultures, instruments, notation, things like that. But one of the key differences is that they use different musical scales. They make different choices about notes. What is a scale? A scale is a collection of notes, increasing or decreasing in pitch. And for us, we're thinking about them covering a range of one octave, from one frequency to its double, say from an A at 440 Hertz to 880 Hertz. Remember, an octave is from one key on a piano to a next of the same name, 12 half steps. You need to know that the names here, the scale notes, are numbered as well as named. The keys on a piano have names. They're A, B, C sharp. Those are the keys on the piano. But when we talk about scales, we also give them numbers. We talk about the bottom one, the fundamental, and then the second, the third, the fourth, the fifth, on and up through the seventh, and finally the octave. Now, some of those are major, some of those are minor. Sometimes we call the fourth and the fifth perfect, but they're numbered. We also have this system called the solfege system, which is do, re, mi, fa, sol, la, ti, do. You, of course, know that from The Sound of Music. Now, the number of notes on a scale is key. We talk about the number of notes on a scale as being the number of notes before you get to the next octave. When you play a scale, you usually start on the bottom and get to the next octave. But if we have a 7-note scale, what we'll call a heptatonic scale, there will actually be 8 notes when you play it because you also include the 8th note on the top end. Now, here's a really important fact about the names on a scale. The piano keys are fixed. There's sort of a fixed reference point. You never change the names of the piano keys. However, the numbers that we talk about, the fundamental, the second, the third, fourth, those are a sort of measurement that keep changing. When you're in the key of C, C is where you measure from. And when you're in the key of G, G is where you measure from. Solfege works the same way. The do changes. It's always called do, but the note name, if we're on a piano, the name of the note, do might stand for an A if we're in the key of A, and then do, re, mi, fa, sol from there. Or maybe if we're in the key of D flat, then the do is D flat, and the re is higher than that, on and on. When we talk about the key of the scale, we're not talking about a piano key. We're talking about the lowest note of the scale, usually first. When we get to compositions, when we talk about the key of some piece, that's the note that's most important, and pieces usually tend to start and end on that particular note. Now, an interval is the distance in pitch between one note and another. It's certainly related to scales, and in numbers, it's the following relation. The fifth, the interval of a fifth, is the distance between the fundamental and the fifth note on the major scale when starting on that fundamental. So let me play you an example of a scale. Here's a 7-note, a heptatonic E major scale. I'm going to play it starting on my open E. That's the basis for Vivaldi's Spring. And here's a different scale. Here's a 5-note pentatonic G major scale. That scale is the basis for Lady Mengjiang, the Chinese piece that I played at the beginning. Now, major versus minor, that's a matter of mood, and we're going to hear the difference between those in a minute. First, I want to make the mathematical connection between these. Remember, the overall goal, the central question in this entire course, is how does mathematics inform the musical experience? The main point of this lecture and the next is the following. How does the harmonic series inform our choice of scales? How we tune these scales, and the implications of those choices, of which notes we put in and how exactly we tune those. These next 2 lectures, this and the next, are each in 3 parts. Today's lecture, we're going to start by answering the question, why doesn't the obvious solution work for constructing a scale? And the key idea here is that octaves and intervals are multiplicative, whereas overtones are additive. Then we're going to look at 2 methods of constructing scales that do work in different ways. The first method is going to be to choose scale notes based on the fundamental. So whatever that fundamental note is, we're going to choose scale notes based on that. The second method is to choose one scale note based on the previous, and then to use that to choose the next one, and to use that to choose the next one. This is some sort of bootstrapping idea. And when we choose how many notes and which ones in different ways, those actually give rise to different moods, and those are adopted by different cultures. A bonus today is we're going to find out why pianos are never in tune. Now, if you're like me, you might know somebody who has the title piano tuner, and you might think that this is going to be really depressing when you tell that person. No, piano tuners know all of this very well, and in fact, they're very good at avoiding the problems that we're going to talk about today and in later lectures. In the following lecture, we're going to talk more about scales, and that's also going to be in 3 parts. First, we're going to talk about how exactly to tune a scale. So for instance, where exactly should I put my fingers on the string to get a beautiful sounding E major scale like the one I just played? Secondly, we're going to talk about the mathematical reasons why 12 is a really good number of keys to put in an octave. On the piano, we have 12 different half steps before we get to the next octave, and there's a mathematical reason why 12 is chosen. And the third thing we're going to talk about next time is how changes in tuning mirror changes in composition, how math made modern music mad, or at least irrational. So let's play examples of a bunch of different scales. And I just want you to listen to these 6 different scales. I'm going to play them both up and back down. Now these are all based on the harmonic overtones, and I'm going to play all of these in A. Here's an A major scale, a standard Western scale, sometimes called a diatonic scale. It's major, it's bright and happy. And here's an A minor scale, also heptatonic, 7 notes before you get to the octave. And this has a mood that's more dark, a little bit sadder. Here's an A major pentatonic scale. Chinese music might be based on something like this. And here's an A minor pentatonic scale. If we add a single note to that, we get something like a blues scale, where the note we're adding is the augmented fourth that you've heard in Maria and the Simpsons theme. And here's an Arabian scale. We heard this at the end of last lecture when I played a piece of Tchaikovsky for you. Now, all of those scales have sort of a different feel, a different mood to them. But one of the things they all have in common is they all have the fifth and the octave. Now remember, those are the second and third harmonics that we hear when we're vibrating just a single note or a single column of air. And the fifth and the octave are almost universal. Nearly every single musical tradition we have on earth contains both the fifth and the octave. but I did want to talk about one musical tradition that doesn't have those. In Indonesia, they use an instrument called a gamelan. And they play scales that are not based on the harmonic overtones that we're used to. Here's an example of a scale on a gamelan played by Mike Simpson, the director of Inspireworks. One of the things you might notice about it is if you compare it to one of the scales we heard before, there's no perfect fifth in the gamelan scale, and there's no perfect fifths used in Indonesian music. There's actually a mathematical reason for this cultural fact. You see, when you look at vibrations of bars, they don't vibrate in the same modes that strings and tubes of air do. They have a different overtone series, sort of like the timpani had a different series. And when you look at that series, since the music of Indonesia is based on the gamelan, their scales are based on the overtones of the gamelan. And so because the bars do not vibrate with a fifth, Indonesian scales don't have a fifth in them. Let's go back to Western scales and review what we need in order to construct these scales. We know that objects vibrate in different modes, overtones, and we know that the most common, the wavelengths of those overtones, are in a ratio of 1 to 1/2, 1/3, 1/4, the harmonic sequence. And the frequencies are just multiples, 1, 2, 3, 4. Those are arithmetic sequence. What we learned from the overtone series is that to go up an octave, you're multiplying frequencies by 2. And to go down an octave, you're dividing frequencies by 2. Also, we learned about a fifth. 7 half steps on a piano is a fifth. And to go up a fifth, you're multiplying the frequencies by 3 halves. To go back down, you're dividing by 3 halves. Let's look at a numerical example just to make sure we understand this. If I play an A, a 440A, what is it to go up an octave? We have to multiply by 2, and we get 880 hertz. If we start back at the A and want to go up a fifth, 7 keys on a piano, going up the fifth, that would be the fifth note on the A major scale. And going up a fifth gets us to the note E, E5. And to figure out what the frequency of that is, we take 440 hertz and we multiply by 3 halves, and we get 660 hertz. If instead we wanted to go down from an A4, a 440 hertz A, to go down 7 keys, we're asking A4 is the fifth note on what major scale? The answer to that would be it's the fifth on a D scale, a D4. And to figure out the frequency of that, we take 440 hertz of our A and we divide by 3 halves, which is the same thing as multiplying by 2/3, and we get 293 1/3 hertz. The octaves and the fifths are the key ingredients we need in order to construct our scales. Now, different cultures have different music, and I think you've heard the different moods that they create. And they have those in part because they choose different scales, they choose different notes, and those choices are at least partly mathematical. And so today, one of the questions we're asking is, how might we choose the notes on a scale? First, we're going to talk about why the obvious solution to that fails, and then we're going to look at 2 different methods that actually succeed. So let's think about building a scale starting with a 100 hertz note, roughly a G2. Now the next octave is 200 hertz, a G3. So we could ask ourselves, if we're trying to build, say, a 5-note scale, why not equally space those notes between 100 and 200? What you get is a 5-note scale, and those frequencies, if you want to evenly space them, it should be 100, and then 120, 140, 160, 180, and finally 200, and that would be a 5-note scale. Again, it has 6 notes because we're including the octave. Let's listen to that scale. That sounded a little non-standard, but let's keep going with this. Let's take this pattern up an octave and go from 200 hertz to 400 hertz. Every time, again, our pattern was that we're going up 20 hertz at a time. Now between 200 hertz and 400 hertz, that's between a G3 and a G4. That's more of a tenor voice, not so much a bass voice. If we go up 20 hertz at a time, we go 200, 220, 240, 260, all the way to 380 and finally 400. And there are actually 10 notes in there, not 5. Let's listen to that part. Those notes are sounding a lot closer together in pitch. But let's keep going. If we go from 400 to 800, we've now moved on to female voices. And we've moved on to those female voices we're going from a G4 to a G5. This is maybe a mezzo-soprano voice. And if we continue doing up 20 hertz at a time, well, we're going 400, 420, 440, 460, 480. We have to go a long time before we finally get to 780 and 800. There are actually 20 notes in the octave between 400 and 800 if we do things this way, not 5 or 10. Now this would be very strange. Higher voices would have more notes available to them in their octaves. You know, it really should be the same number of notes. It would be very weird if you wrote a song for a soprano, but then tenors couldn't sing it because some of the notes weren't included in the scale that you were using. Think about trying to sing a song like Happy Birthday with everybody together. You couldn't do it because some of the notes for the sopranos might not exist for the tenors or for the basses. The key problem is this. These intervals and octaves have a multiplicative structure that we've talked about before. You shouldn't be adding the same number each time. You should be multiplying by the same number each time. If we go back to 100 hertz, roughly a bass voice, if you put a 150 hertz note on the scale, think about that, that's exactly halfway between 100 and 200, at least additively. But if you put a note there, then you see that 150 hertz, we shouldn't think of it as 50 hertz more than 100, we should think of it multiplicatively. 150 is 3/2 times 100. It's a multiplicative structure. Where should we put the corresponding note for tenors in between the 200 and the 400? Well, we could use the same multiplicative structure. If the note we added was 3/2 of the fundamental, let's take 3/2 times the new fundamental, which is at 200. So for tenors, let's take 200 times 3/2, and we get 300 hertz for the note in the tenor octave. Now we note that this is going to work really well. See, the note we gave to the basses was at 150 hertz, and the new note that we have for the tenors is at 300 hertz. That's a doubling, and so those are exactly in octaves again. Where would the corresponding note go for a female voice between 400 and 800 hertz? Let's do the same thing again. Let's take 400 and multiply by 3/2. That gets us to 600 hertz. Again, the notes we've added now, we added a 150 hertz note for the basses, we added a 300 hertz note for the tenors, and now we have a 600 hertz note. Those are all in octaves. It's a doubling to get from one to the next. Sticking to this multiplicative system works. It puts corresponding notes in each octave, and it actually does something that mathematicians love to do. It reduces the problem to looking at a single octave. If we can figure out where the notes go in a single octave, we can use the multiplicative structure to get those same notes in octaves higher for sopranos or in octaves lower for the bass and the male voices. This is a very mathematical trick to do. Instead of solving one problem, you reduce it to a simpler problem and then you solve that. With our reduced problem, we're trying to determine the scale notes for a single octave, and then we're going to use the multiplicative structure, multiplying by 2 and dividing by 2 to get the rest of the notes. Remember that the fundamental underlying problem here is that all of these intervals have to be multiplicative, even though the overtones that we saw earlier were additive. In terms of intervals, we want to use the multiplicative structure. Remember that a piano is actually a logarithmic scale. Equal spacing on a piano, those are ratios, not differences. So how should we go about choosing the scale notes for a single octave? Our first idea, and the first way we're going to go about this, is to use the overtone series of the bottom note to determine the higher notes. And this is something called just tuning. Things are justified, in some sense, by the lowest note. Let's find the notes on an A major scale. If we play an A4 at 440 hertz, we know we can figure out what the overtones are and which notes those are. We worked on that last time. The problem is most of these notes are in the wrong octave. We have the A4, and then we have the A5, that's the second harmonic, and then an E6, an A6, a C-sharp 7, an E7, this mysterious seventh note, which is close to an F-sharp 7, an A7, and finally a B7. Most of those notes are not in the octave we want, which is between A4 and A5. Now, instead of working with 440 hertz, let's talk about relative frequency. And so let's just treat the A4 as 1. And if we do that, we're looking to get relative frequencies between 1 and 2. And to do this, we're going to make use of going down an octave, which is dividing by 2 in frequency. So one of the notes we have on the overtone series of the A is an E6. An E6 isn't the note we want. We actually want an E5. That's in the correct octave. But to get from an E6 to an E5, we're just going to go down an octave, which is dividing by 2. And E6 is the third harmonic above A, and so it has a frequency 3 times the A. So we're going to divide that in half, and we get our E5 of 3 halves. Again, that's the 3 because it's the third harmonic of A. That's in the wrong octave. We divide by 2 to get 3 halves. We can do the same thing with a C sharp. C sharp is the 5th harmonic, so it's 5 times the frequency of A, but it's 2 octaves too high. We divide by 2 twice, and we get 5 divided by 4, 5/4 for our C sharp. For our B, we have to go way out to the very end of the notes that I've talked about. The 9th harmonic is a B, and we have to bring that down 3 full octaves. And so we take 9 divided by 2 3 times, and you get 9/8. You can do this as many times as you want, and you can take as many of the overtones of A and bring them down into an octave, and you get what's called a just scale. So let's look at a just-tuned pentatonic scale. To get 5 notes, we have to do just the notes we talked about in the last section. We have to take, let's see, an A, that's the fundamental, but then the second one is also an A, we already have that. The third one is an E, that's a new note. The fourth is an A again. The fifth is a C sharp. The sixth is an E again. The seventh is an F sharp, sort of, at least that's the closest note on our scale. Finally, the 9th note, the B, is the 5th note that we have. And so to get a pentatonic just scale, we have to take harmonics 1 through 9. Because of the dupling, because of the duplication of those, we need all of those first 9 to get just 5 notes in a just pentatonic scale. And we're going to get those in the right octave by dividing by 2. Now in this chart, you can see both the frequencies and the wavelengths. And we put the wavelengths up here because you can actually do a little detective work with the wavelengths. Given the relative wavelengths, you can tell exactly where each note is coming from. Let's look at B. On this chart, it's 8/9. So the wavelength of a B is 8/9 compared to the wavelength of the A. From the denominator, you can tell it was the 9th harmonic. That was 1/9. And the numerator is 8, which is multiplying by 2 3 times. And so that tells you we took the 9th harmonic and moved it down 3 octaves. So let's look at the just pentatonic scale. What's wrong with this just pentatonic scale? Well, let's play it for you. Here again is A, B, C sharp, E, and then something like an F sharp and A. If you have a musical ear, you'll notice that the F sharp is very sharp compared with the standard Western scale. That's because it's not one of the notes on our piano. And that's why we had to put the piano hammers in a particular place. Now the nice thing about this just pentatonic scale is everything is perfectly in tune with the A. The downside of this is that these notes are not necessarily in tune with each other. Let's look at what this means. In particular, let's look at the B versus the F sharp. Now remember that the B that we've arrived at, in terms of frequency, we've arrived at a 495 Hertz B. That B has its own overtone series. And so when we play the B at 495 Hertz, we also hear its first overtone, its second harmonic, at 990, and its second overtone, its third harmonic, at 1485. Now roughly those are a B, and then the octave, the fundamental is a B, the octave is a B5, and then the next overtone is an F sharp 6. But the F sharp that we've decided on for our scale, the F sharp 5, has its own overtone series. Now we've decided on the fundamental frequency for that F sharp of 770 Hertz. Its first overtone is going to be 1540. And its first overtone should be an octave above. It should be an F sharp 6. Now we have a real problem because one of the overtones of the B is an F sharp 6 at 1485 Hertz, and one of the overtones of the F sharp is an F sharp 6 at 1540 Hertz. Those are very different. Those two notes would sound bad together. We're going to talk about this later. They would produce what's called dissonance. We're going to talk about that in lecture 6. The overtones of the F sharp 6 should match up, but they don't. Let's say this a different way, this B to F sharp problem. You see, the F sharp should be the 5th note above B. It should be a 5th above B. It should be exactly 7 half steps above B. The F sharp should have a frequency, therefore, which is 3 halves times the frequency of B. That's what it means to go up a 5th. We know what the frequency of B is. We've pegged it at 495. We can multiply by 3/2 and we get 742.5 hertz. That's very different from 770 hertz. This tells you that there's a real problem with tuning in general. The B and the F sharp, you can tune them to be perfectly in tune with A, but you can't tune them to be perfectly in tune with each other. Now this just tuned pentatonic scale that we've created, it's great if you're only playing each note with the fundamental, because those are perfectly in tune. It's a very bad scale if you want to play notes with each other. Let's move up and add a couple of notes and move up to a 7-note scale. If we go from a 5-note pentatonic scale to a 7-note heptatonic scale, again, the philosophy here is we're building on the overtones of this fixed reference point of the A, and then we're bringing those back into the correct octave by dividing by 2. We get here an A major just heptatonic scale. And you see the frequencies have these nice fractions. Now the Pythagoreans thought that sounds sounded really nice when the ratio of their frequencies was a fraction with a nice small denominator. And you can see that most of the fractions in this just heptatonic scale are nice fractions with small denominators. These are pleasing sounds. We're going to talk more about the Pythagoreans next time. The 2 notes that I added to this, however, when we went from the pentatonic to a heptatonic scale, are actually not quite right. I'm not telling the full story. And in fact, the numbers are giving away that I'm not telling the full story. You see, mathematically, we can look at the D and the F sharp, and they can't have come from this process. Just think about the relative frequencies here. When you look at the harmonics of an A, you're multiplying by n, right? We're repeatedly adding, and that's multiplying by n. And then the octaves below that, we're taking one of those and dividing by 2. That tells us that every note we get through this process has to have the form n divided by 2 to the k. There's no way of getting 4/3 or 5/3 from this process, because 4/3 and 5/3 are not of the form n divided by 2 to the k. The trick that's used here to get a heptatonic just scale is the fact that D does not appear on the overtone series of the A, but on the overtone series of a D, there are other A's, and so we can tune the D so that the overtones of the D match up with the A. There's actually great music built on this philosophy of just tuning. It's not what we use standardly on pianos, we'll talk about that later, but it is really good for wonderful music, and so I want you to hear some of that. The key question in order to figure out if your musical tradition should use just tuning or not is whether or not you should transpose, whether or not you should modulate, and this is switching keys. And I want to demonstrate that by playing probably the first piece that I ever played. Now, when I was 4 years old, I learned how to play Twinkle, and here's Twinkle played on an A. We could modulate that up to the key of C. What we're doing is we're just shifting up, and instead of starting out with an A, we're going to start out with a C. Now that's easily recognizable as the same melody. It's just starting on a different note. Switching keys, remember that the key is the bottom note of the scale. And it's the note that a melody keeps coming back to. It's usually the first and the last note of a melody. So switching keys is just saying, oh, instead of starting on this note, I want to start on this other note. If you're not going to do any transposing, and if you're not going to play multiple notes at once, just notes played with the fundamental, then just tuning is really wonderful. On the other hand, if you want to modulate, if you want to be able to switch keys, or if you want to play chords where you're going to play notes, 2 notes that are not the fundamental together, then just tuning is not the way to go. It leads to awful problems, like the B and the F sharp that we were talking about a minute ago. But there are cultures where they have used just tuning, and one of them is the bagpipe in Scottish culture. The bagpipe always stays in one key. It has a drone, it plays this fundamental, and possibly the 5th. And that fundamental, that drone goes on, it just keeps going, and you always hear that under a bagpipe. It's the chanter, it's the recorder-like part that gives you the higher notes, the 1 note at a time. There's no problem with this. There's no problem like the B and the F sharp that we had a minute ago, because the chanter is simply playing 1 note at a time, and it's never playing 2 of those notes. And therefore, a bagpipe is properly tuned as just tuned, where the notes, the higher notes, are exactly tuned to the overtones of a drone. So in theory, all bagpipe notes are perfectly in tune with the drone. Now, if you're like me, I've always thought that when I hear bagpipes, I feel like they're never quite in tune with it themselves. It's a little bit strange. But in theory, they are always perfectly in tune. There's a problem if you're a modern bagpipe player, and that's the electronic tuners you use to tune instruments. Those don't use just tuning. They use an equal tempered system. We're going to talk about what that system is later. So let's hear an example of a bagpipe tone, and I want you to listen to the low drone notes that never change, and how the higher melody is tuned to those overtones exactly, the overtones of the drone. Those are the Scottish bagpipes. I want to talk about another musical tradition where just tuning is exactly the right thing to do. In Indian music, they play with instruments like the sitar and the tabla, and Indian music always stays in one key, and it also has a drone that's playing a low note, and it's playing that note throughout the entire piece. The melody is then played on top, one note at a time, above the drone. And each scale they're using, they call them ragas, each scale has its own particular tuning. Each scale is matched to different overtones of the fundamental. And they have different sets of overtones to choose depending on which raga they're using. If you're interested in this, one of the recommended readings by Forster has an in-depth section on Indian tunings. So depending on the mood you're going for in a particular Indian piece, you may have a sunrise raga, and you might tune the particular notes to some of the overtones, or you might play a spring raga, which might tune to different overtones, but always tuning to the overtones of the fundamental, overtones of the drone. Or if you played a winter raga, you might make a different choice. But in all of these cases, just tuning is used. You're always tuning the higher notes exactly to the overtone of the bottom note. It's a different mood depending on which ones you choose. So let's hear an example of Indian music. And I want you to notice that all of the notes being played appear in the overtone series of the drone, or they're octaves below notes that appear in that series. These notes might not be in tune with each other, but that's okay because they're never played at the same time. The piece stays in the same key the entire time, and that key is established by the drone. So let's listen to a sitar and tabla piece from the Indian tradition. And again, in Indian music, it's always staying in one key with one fundamental and no modulation. You're not changing keys. You're always using just tuning, where each note appears in the overtone series of the fundamental, and you're dividing by 2 to get it in the correct octave. So that's one way to choose notes on a scale. Let's talk about a second way, and that's bootstrapping to go from one to the next. Again, we're going to use the overtone series, 1, 1/2, 1/3, 1/4. In frequencies, it's of course 1, 2, 3, 4, 5. The old philosophy was just to take A as a fixed reference point and build on the overtones of A. The second philosophy is going to be to take the A and use that to get a note, and then to take that as the new reference point and get another note, and take that as a new reference point to get another note, bootstrapping from one note to the next. The idea is that the overtones of each note should be included in the scale. And it's not possible to include all of them, but we're going to try for the most audible. So remember that the most audible intervals that you hear are the octave and the fifth. The second harmonic is the octave, and the third harmonic gives you the fifth. So if we want to use this philosophy, we're going to have to include the octave and the fifth. So let's start with A and try to apply this new philosophy, adding overtone notes. Now we start with A, and the third harmonic of an A is an E. We're going from A to E. E is the fifth note on an A major scale. Here's an A, here's an E, and you note it's the fifth note on a major scale. Okay, now we've added a note. Now here's our scale so far. You can't make really interesting music with just those notes. So let's add another one. Let's look at the E and look at its third harmonic. If we look at the second harmonic, that's just another E, an octave above. But if we look at the third harmonic above an E is a B. And so that, once we bring that into the correct octave, that gives us another note. Still not enough for interesting music, so let's keep going. Now let's look at the B, bootstrapping along. The fifth note above E, a fifth above B, is an F sharp. Let's put that into our scale. There's still a gap in there, and so let's add one more note. For music folks, if you know this, we're just walking around the circle of fifths. We're going to talk more about that next time. So the third harmonic of the F sharp is a C sharp, and now I think we might have enough notes to play interesting music. What do we have? We have a pentatonic scale. Let's hear the pentatonic scale. That's a nice pentatonic scale. We heard some Chinese music based on a pentatonic scale like that earlier. In the Western tradition, some composers really like the pentatonic scale. Carl Orff, who composed Carmina Burana in 1937, he thought it was a really wonderful scale for children, in part because it's a very simple scale and you can improvise in a pentatonic scale and everything sounds quite good. It's simpler, there are fewer choices to make and fewer of those choices sound bad. The nice thing about this scale, about a pentatonic scale, is the notes sound consonant. You've matched overtones from one to the next. One of the problems is that while we've gone from one to the next, we've ended with a C sharp. The second overtone above a C sharp is a G sharp, and that's not on our pentatonic scale. But still, a pentatonic scale is good enough for producing interesting music. So let's look at some of that music. Chinese music uses a pentatonic scale, and the piece I played at the beginning is exactly an example of that. The piece is called Lady Mengjiang. In Mandarin, it's called Mengjiang Nu. And it's a folk tale about the Great Wall. Lady Mengjiang was a woman whose husband was sent off to help build the Great Wall, and he died while he was doing that. And when she found out about it, she went to the Great Wall and she cried, and her crying brought down a whole section of the Great Wall. That's the story behind Lady Mengjiang. Now at the beginning we heard it on violin, I played it for you. Now I want you to hear it on the traditional instrument it would be played on in China, which is called an erhu. It's a two-stringed Chinese instrument, and the timbre is very different from a violin. The box on an erhu is very much smaller, and it's different from the wooden box on my violin. And because of that, those two things have different resonances, and it gives it different timbres. But the key here is a G major pentatonic scale, and that's the scale that's used in Lady Mengjiang. Now, as you listen to this, I want you to think about a few things. I want you to think about the philosophy that led to this particular pentatonic scale, how the overtones of each note gave you the next note, and we bootstrapped our way until we had 5 notes. It's such a beautiful piece, played on its original instrument, the erhu, and I also want you to think about that, how the distinctive timbre of the erhu is something that you can hear because your ears are doing a Fourier transform. So let's listen to Lady Mengjiang. Pentatonic scales aren't just used in Chinese music or other cultures, they're actually used in Western music as well. And I wanted you to have a chance to listen to an example of that. So let's look at Dvorak's Ninth Symphony. Now this is called the New World Symphony. Dvorak composed this after he'd spent some time in Iowa, and he was drawing on Native American and African American musical traditions, some of which included pentatonic scales. I want to listen to the second movement. It's a lush, beautiful, it's a very famous movement in classical music. And what I want you to hear is that this melody is based on a D-flat major pentatonic scale. I want you to ponder the choices in choosing the next note based on the previous one, leading to a pentatonic scale, and the mood set by those choices. So let's hear the main melody from Dvorak's New World Symphony, the second movement. Oh, it's such a wonderful, beautiful melody. Dvorak chooses a different timbre rather than the violin to play this. It's a different pattern of overtones. Think about the spectrum. The instrument he chooses in order to play this melody is actually the English horn. Now, the English horn is probably the instrument in the orchestra whose spectrum is closest to a human voice, and he chooses the English horn for the statement of this theme, giving it this really soulful, melancholy sound to it. It's maybe one of the most beautiful melodies in all of classical music. So let's listen to that. Let's listen to the English horn playing this melody from Dvorak's Ninth Symphony. Oh, that's such wonderful music. So that concludes our discussion of these pentatonic scales. I want to last talk about why pianos are never entoed, and why this bootstrapping idea, getting from 1/5 to the next, actually proves that. Let's think about a piano. We have a piano right here, and let's think about trying to tune it. So we're going to start in the bottom note. The bottom note on a piano is here, it's A0. And the idea is we're going to bootstrap up a fifth every time, tuning the fifths exactly. Remember, to go up a fifth, we're multiplying the frequency by 3/2. Every time we go up a fifth, we're going up 7 keys on our piano. You need to take the frequency of the previous note and multiply by 3/2. And so we have an A down here on the bottom, and then the fifth above that is an E, and then a B, and then an F sharp, and we can calculate the frequencies these should be at. The A0 should be at 27.5 hertz. The E1 should be at 3/2 times that. You get 41.25 hertz. The B1 should be at 3/2 times that. You get 61.875. At some point you realize we should be a little bit smarter about this and use the tools of mathematics and use exponential notation. So let's call the F2, the F sharp 2 here, should be 27.5 times 3/2 to the third power. And you get 92.8125 hertz. The C sharp 3, that's the next one, should be 27.5 times 3/2 to the fourth power. And the next one is a G sharp, and that's 27.5 times 3/2 to the fifth power, all the way on until you get up here to an A7. And the A7, according to our calculations, should be 27.5 hertz times 3/2 to the 12th power. But again, like any good math students, we should check our work. So let's see. See, we started down here at an A0, and we ended up here at an A7. That's 7 octaves above the A0. And we know how to go up an octave. To go up an octave, we should be multiplying frequencies times 2. And so we have 27.5 hertz. That's for A0. A1 should then be 27.5 hertz times 2. A2 should be multiplied that times 2 again, 27.5 times 2 squared, all the way on until we get to A7, which would be 27.5 hertz times 2 to the 7th power. And now we've checked our work. Except the answers we got, the fifths were 27.5 times 3/2 to the 12th, and the octaves were 27.5 times 2 to the 7th. The problem is that those are not the same numbers. That's the problem when we try to do this. If you think about it in terms of number theory, the left side of this equation, 3/2 to the 12th, has powers of 3 over powers of 2. There's no canceling in that fraction, whereas the right side is an integer, 2 to the 7th. When we pull out a calculator and get numbers, 3/2 to the 12th is 129.74 about. 2 to the 7th is 128. Those are simply different frequencies. The question is, how should you tune this top A7? Should you tune it, make it in tune with all the other fifths, or should you put it in tune with the octaves? The important point here is you can't do both. You either tune your fifths in tune or your octaves in tune, but you can't have both of them perfectly in tune. No piano is ever in tune, and we're going to talk about that more next time. Now, this is a really well-studied problem, and the history of mathematics includes parts where people are dealing with exactly this problem. Marin Mersenne, a French mathematician in the 1600s, wrote about this problem. Hermann von Helmholtz wrote a large tome in German in the 1800s about this. And both of them are essentially saying, we can't have everything in tune, so what are we going to do to get close? That's what we're going to talk about next time. How exactly do we tune the notes on our scales? To close, I wanted to return to Dvorak because it's such a beautiful piece. And let's listen to Dvorak's Ninth Symphony again. This is later in the piece where the orchestra is reduced to a string quartet and eventually just to 3 instruments, a single violin, a viola, and a cello, on a stage with many other instruments who are quiet at that point. This is one of my favorite pieces to play in an orchestra. I want you to think about how every musical tradition chooses their scales differently for their particular music, and how those choices are very mathematical in nature. So here again is Dvorak's Ninth Symphony, the second movement. Thanks for joining us.